we are wrapping up fuel cells, everyone. So next week we will dive straight into life cycle assessment and sustainability, circular economy of fuel cell materials. We could focus on all the materials, but we can't. So we'll focus on the most critical material, which is platinum catalyst and fuel cells, and then we'll move on to life cycle assessment of lithium-ion batteries, specifically for the transportation sector, and also recycling of lithium and its components, lithium-ion batteries and its components. So lithium metal itself, lithium salts, and then also looking at batteries from cradle to grave. That's basically the buzz term for, really thinking about sourcing of materials and which processes will be most sustainable. But, we'll talk about sustainability, and for the purposes of this class, it is a material within the materials department. We'll focus on the processing, the manufacturing, sourcing, but I should say there's a huge asterisk to everything that I will say, which is the local geopolitical environments of where these mines are, or where you source them from, will have huge implications and on the technology itself. Right now, we've alluded before to this is a huge current topic discussion, but we've talked about lithium from salt, from brine, basically back in huge areas where you just have salt deposits that contain lithium. And right now it's not cost competitive, but the offset of mining lithium in certain areas of the world, including North America, requires a lot of nuanced analysis that, I'm tiptoeing around political discussions that is very loaded. It doesn't have one clear solution, and it requires a lot of voices, because just because you own a mine and you happen to be from the US, and you own an international mine somewhere, doesn't mean you should be able to dictate how the local people should live, so it's very loaded, and because I don't think we can do it justice within the realm of just a materials course, but I do want to make sure that you're all aware that as material scientists or engineers in general, we have to think about these sourcing problems holistically and not just say, how do we decrease one metric, which is cost.
Cobalt is the only element that's like horrible to mine, is that right? Whereas all the others are just dirty and bad for the environment.
Okay, so Alan, you've asked a very yes, it is a very opinionated question. But, we can certainly discuss the quantitative metrics, right? What is dirty? Is it greenhouse gas emission during the refining process? Is it labor laws? Is it politically dirty? You know what I mean? Like
slurry produced leaking back into the environment.
It could be, yeah, like the some of the byproducts of the mining, refinement. It's really loaded. So what I would like to focus on is, as engineers, what we can bring to the table are, scientific, technical discussions and analyses, while also being human, right? I mean, we can be aware of all these, but unless you're a policy wonk, it's be aware of the policies that affect these decisions, such as, if okay, I'm taking too much time. Basically, this is like Wednesday's lecture, but what I'm saying is we live in a society that is globally connected, right? That's the cliche term, but it is absolutely true. Places like Argentina, Chile, a lot of the lithium mines are there. But, you know, as someone who lives in the US, what do I get to say about someone who lives in Chile and whether or not we can dig into their mountains just to get lithium for a company that will make it in Korea, who will then sell the pouches over to Tesla to finally make it. You know, so it takes a lot of voices, and it is not always such a simple solution of, well, don't you see the benefits, right? And the electrification is beneficial. So shouldn't people who own, you know, X mountain or whatever space in the mountains of the Andes or something just comply for the better of the, you know, the world, you know? And we all live locally, as in we are very present with the issues that, the economic issues at hand in our own lives, right? You know, we all go home and can we put food on the table, things like that. These are what people are really concerned about. So, you know, we have to take that into account with the materials and the technologies that we develop as well, right? So it's very much complex, but that's all to say, there's a lot of opportunities for us as engineers to invent a pathway that doesn't have to look like the past. It doesn't have to look like, let's put technology first and everybody is just going to fall in line to push that technology. That used to be the case. It doesn't have to be the case anymore. And you don't have to follow that pathway. You can totally come to the table with different solutions that doesn't require, like, let's blaze a path that just, you know, and everything falls to the wayside, right? So, so we'll talk about that. But technically, in technical terms, of course, you know, otherwise this becomes a political science class or macroeconomics class, for which I am not prepared to discuss or teach. So, yes, anyway, so we'll wrap up with fuel cells. Your proposal is due within a week's time, plus a few hours, because the timestamp is 11:59 p.m. Several of you have reached out and asked very specific questions in the context of also very general questions. So I try to do as best I can to copy and paste that to the discussion forum. So once again, please see the discussion forum. If you have any questions, start from there. And if your questions are not answered, feel free to reach out to us again. So that's basically it. Okay. Any questions before I start? Okay. Fuel cells, solid oxide fuel cells. We've gone from polymer electrolyte membrane fuel cells that are more portable. They have a smaller footprint. Today we'll talk about solid oxide fuel cells. So they generally have a larger footprint in terms of the stack sizes. Dagny asked, about Nafion, so I wanted to answer her question before we go. Basically, your question was, well, why don't we understand, the structure of Nafion at this point? Or what's the real controversy, in understanding this material and how to design it? And my answer was, well, there's a lot done there. It's highly controversial. There's a fabulous 48-page paper that is a review paper on how to interpret these broad peaks in the soluble X-ray scattering for designing, for engineering Nafion as the membrane under different humidity conditions, right? And so there, the electrode materials play important roles. Understanding the electrolyte plays an important role, and that will be the same case here for solid electrolyte fuel cells, which is the solid electrolyte also plays a huge and important role in ion conduction. But the ion that we'll talk about here is actually oxide. So oxygen O2 minus conduction, as opposed to what we were talking about before, which is proton conduction. And so we'll start off with that. Olivia also had a question about how big these things are. Well, to clearly show you how big or small these stack sizes can be, you can see here, this is an example that I took from Getty Image from a particular photographer, this David Paul Morris person. So giving credit where credit's due, but not my photo. Yeah, so that's the solid oxide fuel cell stack in a particular vehicle. So the width of the photo is, basically most of the vehicle, but it can be as large as, depending on your application, it can be as large as that. And here's the human, by the way, from this photo. So that gives you a sense of, how big can you scale these fuel cells, and how big can you make these stacks? Very big is the answer.
Probably helps that the fuel source gases half the time.
Yes, well, I don't know about half the time, but some of the time they are gases, as in, methane or hydrogen, but sometimes they are liquid, so methanol, even higher hydrocarbons like, ethanol, but that makes it more difficult because then you have to reform the alcohol into hydrogen. So this market is just going to continue to grow. You can see here the projection. So here, if you're looking, where can solid oxide fuel cells grow? It takes a huge part of the market, and it's estimated to just keep on growing, as you can see here, and in a variety of sectors, I might add. So first, it's mostly stationary, projected to be for mostly stationary, with some for transportation, and then portable applications. Potentially maybe, I don't know, laptops or whatever. But that's where the major uses of solid oxide fuel cells are going to be. These cells can actually be quite thin, and that's what we talk about. We'll talk about, developing nanometer, like hundreds of nanometers, thin electrodes, electrolytes, to millimeters. And then you can combine them in a stack. So that's what you see here. So here you could have one cell that produces 25 watts of power. So that can power one light bulb. So I took this from Bloom Energy, who's a huge producer of fuel cells. They really are a huge player in this area. So you can see one fuel cell can be 4 inches by 4 inches. The stack thickness is not that much. Each component, is cathode could be a few microns, anode could be a few microns, electrolyte a few microns. So that's how thick a cell is. I mean, it's not very thick. Even with the casing, you can get it quite thin. And then you can stack a bunch of them together to get something like 1 kilowatt, right? So this right here in the palm of your hand can power a home. Right? And then if you think, okay, well, if that can power a home, well, how many or how big are these stacks going to be if I need to power, let's say, like a refrigerator or a storefront? You need a module. So here's a person for size comparison. So you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then if you need, more than that, at let's say 100 kilowatt. So for these modules, so it's the size of a parking space for reference. So you can build yourself a tiny house that's the width of a parking space, or you can have a stack of fuel cells here. And that can power a 30,000 square foot home or office, office or 100 homes. So that's the scale we're talking about. So they're quite efficient, and the technology now, we can make thin film electrodes. It doesn't actually require that much footprint. So the photo you saw before was an old photo from Siemens Westinghouse where that was combined with a gas turbine. I don't actually know how much of the gas turbine is of that footprint, but it makes the footprint much larger. Right. So everything about solid oxide fuel cells that make it attractive are, well, fuel flexibility. So here, you can feed in not just hydrogen, but methane and other type of fuels. We'll talk about the catalyst material on the anode and the anode and the cathode side. Right. High power density relative to polymer electrolyte fuel cells, and does not require membrane hydration. So this is specifically in contrast to that of polymer electrolyte membrane fuel cells, where the Nafion does have to be hydrated to some extent. Of course, some of the fabrication techniques are a little bit pricey. Ceramics processing can require high temperature, so that requires high temperature furnaces. But so that can be a limiting factor. And of course, with all fuel cells, you need to seal because these cells, because they have to operate at 600 to 800 C, right? So they just can't be, well, one, they have to be sealed for also safety purposes, right? That you can't have exposed cells at like 600 C, that's kind of dangerous, right? And of course, they operate at high temperature, 600, 800 C, but there's a lot of progress being done to bring down that temperature to 600 C and maybe even a little bit below, like maybe 500 C, maybe even 400 C, right? So problems that are not insurmountable, but some of them are limited by materials, as in if you want high ionic conductivity, specifically high oxide, O2 minus, conduction of O2 minus, you need to be operating at elevated temperatures beyond 100 C. And a lot of materials, especially in ceramics that we're going to be talking about, there is a limitation to that, so you have to start thinking about, well, how do I introduce vacancies to like increase ionic conductivity, to decrease the delta G, decrease the energy of migration so that my O2 minus can proceed at lower temperature. So that there's a lot of ceramic processing that go into material design for this reason. So that's the majority of what we'll talk about is the diffusion O2 minus, how to engineer these ceramic materials so that ionic conductivity can be higher, and then also assemblies, how do you make a solid oxide fuel cell? Okay, so, but first, the fundamental mechanism of like, what is a fuel cell, what happens at the cathode and the anode, that's summarized here, right? So at the anode, you still have oxidation of the fuel. Before we talked about oxidation of hydrogen going to protons. At the cathode, you have a reduction of O2 minus, so oxygen reduction reaction, ORR. So these are still the same. But what gets the ion that migrates is O2 minus. Now, I did mention that you can input other fuels. So here you see the input of methane, CH4. What happens though is if you introduce methane, you'll need to reform it. So that's the chemical engineering term where you have to change your fuel into hydrogen. So you reform it into, let's say, hydrogen, but you could see here that one of the products for reforming, so this is called steam reforming, because the other reactant is H2O gas. So this is done above 100 degrees C. H2O is in the gaseous form. So you can transport methane instead of hydrogen. You mix in steam at elevated temperature. You get out 3 molar equivalents of hydrogen here, but you also get carbon monoxide as a byproduct. This is not so advantageous because we don't want to deal with carbon monoxide for safety reasons, but also, it traps in heat. So then what you can do is then you can take that carbon monoxide, add in more steam to produce CO2 and more hydrogen as fuel. But now you just converted it to a greenhouse gas. So these are some of the challenges with using methane instead of just hydrogen. So that's called the water gas shift reaction. That's a pretty popular reaction in chemical engineering. People study, that quite a bit. You can also dry reform methane into hydrogen. So you take your methane, you add in carbon dioxide, and then you can produce 2 molar equivalents of hydrogen, but then you also produce 2 molar equivalents of carbon monoxide, for which you can then process again, through the water gas shift reaction at about 700 C to then produce more hydrogen, but then more CO2. So then you have to ask yourself, well, what are we going to do with the CO2 that's left over? Well, you can do a number of things. You can use it to as a starting material to then make longer hydrocarbons. You can just store it. That's what some people do. There are a number of things you can do. You can also just sell it to the soda stream people. I mean, that's really not a joke. It is absolutely a viable option. So you can sell it for, you know, other types of application that use it. But this is one of the issues that you're going to run into if you do steam reforming or dry reforming of methane to then produce hydrogen on board to feed into solid oxide fuel cell. Okay. So we'll talk about one of the biggest components of solid oxide fuel cells, and that is the electrolyte. This has been a huge area of research from NASA back in the day being, you know, the 60s, the 70s. It's been a huge area of research, and it continues to be a huge area of research because this is what transports your ions from one electrode to the other. So the reigning material thus far is yttria-stabliized zirconia. So you start off with ZrO2. This is what cubic ZrO2 looks like. Cubic zirconia also being, I guess it's known for being like fake diamonds, but it's a huge player in turbine coating. So if you want your metal turbine blade to operate at higher temperatures, you know, like 1000 C or so, then you need to protect the metal turbine blade with a ceramic coating. And so YSZ comes into play for that reason because of all these advantages. It has high chemical stability, high fracture toughness, but in the case of SOFC, what we care about, high ion conductivity, low electronic conductivity. But as a ceramic material, it's also really good for coating applications. The other material other than YSC that people looked at a lot is what's called GDC. So you'll see a lot of this in the literature, this particular acronym GDC. So that is gadolinium doped ceria. So here, both gadolinium and cerium are rare earth metals. So that means mining them is quite difficult. Getting them, extracting them from the earth is really difficult. And some of the mines that are cerium mines are owned by several companies from a multitude of countries, which makes it really difficult, you know, if you're in the US to procure cerium, and the prices really fluctuate based on what's happening in like global politics. Okay, so so that's some of the limitations. But what you see here is why people started exploring GDC as a potential replacement, but really what ended up happening is people make these mixtures of GDC and YSC because GDC also has high chemical stability, also high ion conductivity, also high but you can see here the electronic conductivity also increases with temperature, which is a huge problem if you want to use this material as a solid electrolyte, right? You want the solid electrolyte in the middle to be ionically conductive and transport O2 minus, but you don't want it to be electrically conductive because it's going to short yourself, right? But the mixed ionic electronic conductivity, or MIEC, that is just something that we contend with, you know, when we engineer materials. So it's basically, you know, you look at these ionic conductivity curve and you just think, okay, well, here's my ionic conductivity on the y-axis. Here is temperature. So it's actually inverse temperature. So this is an Arrhenius type equation, Arrhenius type plot. And so you look at it, you say, okay, well, the activation energy for YSZ, so that YSZ is here in this, so it's right here. GDC is in the square. So it does have higher ionic conductivity, but so it's attractive, but the high electronic conductivity is, limits its use at a certain beyond a certain temperature. So what people typically do is they'll just mix the two together, or they make a bilayer. So what typically happens in these cells is you can make YSC one layer GDC and one layer, and then you make your sandwich that way. So you sort of try to make the best of both of or take advantage of the good parts, the metrics that you're aiming for. Oh, there's also all these types of materials that we'll talk about later as well. They're being explored, but they have some challenges that make them more difficult to manufacture, or just not sufficient to supplant YSE as the reigning solid electrolyte material thus far. Okay, so how does ion conduction work? So if you're thinking, okay, well, I want high ion conductivity, what do I do? So you look at the phase diagram, but before you even look at the phase diagram, you think, what is the crystal structure of zirconia? Trick question. What temperature are we at? That was a rhetorical question. That's what you ask when people ask what phase is it. You need to know what temperature you're at, because that is the whole issue with zirconia. It's called yttria-stabliized zirconia because you need to stabilize the high temperature phase at lower temperature. Right. So what people have done is they've substituted zirconium, so the cation site, with an aliovalent substitution. So what that means is you pick a cation with a different oxidation state. So in this case, yttria, so yttrium oxide, or Y2O3. And by substituting with a different oxidation state on the zirconium side, you now also have a vacancy that comes with that for charge balance. So zirconia, the zirconium is 4+, as you see here, right? So zirconium dioxide. So oxygen is 2-, so O2 is 4-, which means zirconium has to be 4+ for charge neutrality. So if you substitute with yttrium 3+, then you need one vacancy for every 3+ to now be charge neutral for 4+. Right, so that's aliovalent substitution. You substitute with a different oxidation state, it comes with a vacancy, and now you decrease the delta G of migration, so you have to overcome the energy hump to then have the O2- pop along. Okay. So then you say, okay, well, why don't I just introduce a whole bunch of these vacancies to move the O2- along? You can, up until a certain point. After a certain concentration of yttria substitution, there's diminishing returns. Then you have too many vacancies. And when you have too many vacancies, they start interacting with each other. And you actually have decreased ionic conductivity. So there's a Goldilocks concentration where you have enough vacancies to increase your O2- ion conductivity, but your lattice is now not full of oxygen cation vacancies, where then the vacancies start interacting with each other. Okay, and that is this 8%, 8 molar percent of yttria. So going beyond that is diminishing returns for increasing your ionic conductivity. Okay. Okay. So how do you come to the conclusion that you should substitute with zirconia? You don't just look at the periodic table and say, well, I'm going to try everything and then see if it works. No, you systematically go through and you say, okay, if I don't want to introduce strain into my material as much, then I should pick a cation that's of similar size as best as I can. But that also adds stability. So if you look at the phase diagram of zirconium dioxide, so here's a binary phase diagram where the components are not just the metals, but the components are the oxides themselves. So here is 0% of Y2O3. So that means it's all zirconium dioxide. And on the right side is 100% of Y2O3. So there's no zirconium dioxide on the right side of the phase diagram. So if you're here, what happens is zirconium dioxide will go from the monoclinic phase, okay, up to, and then it will phase transform at 1173 degrees Celsius to the tetragonal phase. And the high temperature, high ion conductivity phase is this cubic phase at 2370 C. So what you want to do is you want to stabilize this high ion conductivity phase that only occurs at high temperature above 2370 C. You want to lower that down and have the cubic phase be stabilized at much lower temperature, at like 600 C, 700 C. That's where you're operating at. And the way you do that is you substitute in with zirconia. Then you look at the radius, the ionic radius of yttrium itself. So yttrium, if it's coordinating site, then coordination number is 8, which it is. So zirconium is cubic, and that much we know from here. So cubic, so it's actually FM bar 3M, or space group number 225 out of 230 space groups. One of my favorite space groups, I have to say, number 225. So that means the cation has 8 nearest neighbors. So it's bonded to 8 oxygens. So zirconium here with 8 neighbors, or the coordination number is 8, is 0.84 angstroms for the ionic radius. Yttrium, coordination number 8, is 17% away, which is 1.019. So it's a little bit larger. So there is actually some strain in the system now, which will then get me to the next point as to like the search for ions with similar similar radii. But the point is, you can also look for other oxides that you can substitute with to bring down the high temperature phase and have it be stable, the high temperature phase of zirconia, and have it be stable at low temperature. So people have tried calcium oxide, people have also tried magnesium oxide, but yttria seems to be the most stable. It also results in the highest ion conductivity phases of substituted zirconium. Yes, Olivia.
So like talking about like maybe like processing out this. So when you have it, is there any way to reduce strain by maybe like heating it, you know, like reduce the residual strain from that?
Yes, and that's, yeah, absolutely. So people do that, basically anneal it,
Yeah.
right? I mean, you age it and you kind of like let solid diffusion do its thing and let everything equilibrate. You can absolutely can do that. The only issue, so that's for the bulk material, right? So I should say the caveat here is I'm talking about the bulk lattice parameters, also the bulk ionic conductivities. This is not, you know, you make like a pellet and you measure ion conductivity this way. But when you come to making and actually fabricating a solid oxide fuel cells that you see, you know, that can sit in your hand, you know, these stacks of cells that you stack in your hand, you then have to jump over and utilize other processes for making thin films. In the ceramic world, this is pretty thin. You know, obviously, you know, when you're talking about photovoltaics and doing like molecular beam epitaxy to grow, you know, heterojunctions that are like 2 nanometers thick, right? Micrometers relative to that is not very thin, but for these applications, these micrometers, that's actually really thin because you can't go much thinner than what's currently available in this particular geometry, as in like the plate-like geometry set, because what's going to happen is the defects that you have will start crack propagation in ceramics. So if you make it thinner, you have these pinhole cracks that start to form, and then your cell will short. So too thin is actually detrimental. So going too light actually kills the performance of your entire cell. So, you know, increasing or lightweighting doesn't necessarily always equate to the highest performance. Yeah. Mm-hmm. Yeah.
So like, look over there and defect or something like that.
Mm-hmm.
Partially dress up, but like, you're not changing the composition of how it's heat.
I think that Olivia's,
Marks of it, like, shorter.
but you are annealing out potential defects. So the substitution here is not ordered in any way. It's a disordered substitution, as in like you mix in some Y2O3, depending on your synthesis conditions, you know, it's not like you can predictively design, let's say, you know, if I mix in 1 molar % of yttria, that your cubic symmetry, that doesn't mean, you know, that doesn't mean there's periodicity in the substitution. Like, it does not guarantee that 1 yttrium is always X unit cells away or X atoms away. So there's no periodicity for this particular example. You know, for the case of, let's say, copper gold alloys, if you heat up to a certain temperature, you go from disordered, as in like some copper goes into the gold FCC sites, it's not ordered, and then you increase the temperature and all of a sudden you induce order because there's a phase transformation to a particular phase that orders it, where you say, okay, 1 copper will always be 2 atoms away from another copper. It's like copper, gold, gold, copper, you know, so that kind of ordering. But so that similarly, you can, that's a phase transformation that induces ordering. Olivia's question was more about just like processing, where you like let temperature anneal out any potential defects in the growth, in the mixture. So there, the mechanism is just solid diffusion and equilibration over time, which for ceramics, it just takes a long time and high temperature for these components to, you know, move around. Yes, Alan.
So there isn't regular order in the yttria stabilization, it's just filling in the gaps.
There's no order, yes. What do you mean by that?
Vacancies?
Oh, no, the vacancies come with, the vacancies don't ever get filled.
It doesn't fill in the vacancies.
No, yeah. So here you could see, so there's intrinsic vacancy, as in like any material that you find on, you know, on the ground. Like you go outside, you pick up a big chunk of dirt, that any material has intrinsic vacancy. Like it's always, like everything is defective in the world, right? Even if you try to make like an ingot of iron, there's going to be, based on thermodynamics, there's always going to be X amount of vacancies based on the temperature that you're at, right? And we can calculate that based on statistical mechanics, as in, okay, what's the likelihood of having a vacancy in your silicon when you process it at a certain temperature? So that's your intrinsic defect vacancy concentration. This is intentionally introducing vacancy concentration by physically mixing in yttria, and these vacancies never get filled. So
Yttria doesn't fill in the vacancies, it
No.
brings them.
it brings the vacancies. And that is the exact mechanism for why you have high ionic conductivity, because you increase the vacancy concentration, which means you now have additional sites for O2 minus to migrate, because when any ions migrate, whether you're in lithium, right, you're in lithium ion battery world, or you're in the ceramic O2 minus ion conduction world, the ion has to go somewhere. Like it has, whether it goes into an interstructural site, if it can fit there, or it goes into a crystallographic Wyckoff site, it needs a physical like position to go into at the atomic scale, right? So if there's a vacancy, then it can occupy that space and then it can hop along. So when you increase vacancy concentration, you increase ionic conductivity. But there is too much of a good thing. Okay, so here I calculated out how many, with the concentration of vacancies per cubic meter. So the gist is 100 to 100 to 1,000 moles per cubic meters is is a lot. Or I should say, it's a lot for increasing ion conductivity. It's useful for that. Yeah. So, all right. Okay. Oh, there's a plot. There you go. So this is the plot. So people have done studies. So they've measured the ion conductivity, and that typically requires, making a pellet, putting 2 contacts on either side of the pellet that are not ionically conducting. And then you can do what's called electrochemical impedance spectroscopy, which will not be covered in this class because you can also spend a semester studying that. And there used to be a whole semester on electrochemical impedance spectroscopy. But anyway, okay. Yeah, so you can make that measurement and you can back out the ion conductivity, and people have done that. And you can see here that the more vacancies you introduce, the better, up until about 8. Here it's like 7.5, but somewhere between this range of substitution, molar equivalent, so mole percent of yttria, the ion conductivity will increase because of the increased vacancy concentration, and then it will decrease. Okay. So anything beyond this point is, diminishing returns. That's my only econ reference, by the way. So yeah, there you go. And what you see, well, how do you measure this ionic conductivity? That's based on the diffusivity. But what you see here, I write this equation out again because it's the same equation we use for measuring ionic conductivity of lithium ions. So you plot ionic conductivity times temperature is equal to an Arrhenius type relationship, where this is the prefactor. So this is everything, this A is everything before exponential. So that requires you to calculate the carrier concentration, literally how many O2 minus you have in your material, the carrier mobility, the charge of the ion. So are you transporting +1 or 2 minus? But in the end, the Z becomes, absolute value. So it's really the number. So 2, Faraday's constant, F, diffusivity, which you can also measure if you know the activation energy, which we have calculated the activation energy. And then gas constant, T, and the activation energy, well, this EA is usually the Gibbs free energy divided by F. So, well, F being Faraday's constant again. So Faraday's constant is all floating in there. But that's all to say, zirconia, if you just have zirconia at 1,000 degrees and you say, okay, O2 minus, move. The concentration, the intrinsic vacancy concentration that you have there at 800 C, oh, I said 1,000, sorry, 800 C, 1,000 C, some elevated temperature is 0.001. That's the concentration. The extrinsic, if you substitute in with, let's say, 8 moles of yttria, now you've increased the concentration by 1,000-fold. So you've increased ionic conductivity by increasing the vacancy concentration by just substituting in with yttria. Okay. So then we also look at our friend gadolinium dope ceria. So you'll see terms like GDC 10, GDC 20. That's all to say that's 10 atomic percent substitution of ceria with gadolinium. And so the stoichiometry is just cerium 0.9, gadolinium 0.1, because they substitute on the cerium site, the gadolinium. And then this oxygen, it's not always stoichiometric. In fact, it's substoichiometric, as in there are also vacancies on the oxygen site. But it's about 5% or 10% here in this case. And the conductivities are about 0.01 Siemens per centimeter at a higher temperature at, let's say, 500 C. So these are not at room temperature because these cells are operating at elevated temperatures. So you can calculate, so what you'll see in the solid oxide fuel cell literature, but also in the battery literature, whenever you look at solid electrolyte curves, is you'll see the conductivity on the y-axis, and then you see the temperature, but it's always 1,000 divided by temperature. So it's inverse temperature. your x-axis is 1/t. So you can calculate, some curves or some plots are quite helpful, and they have the equivalent, like they've done the calculation for you. And they've computed the temperature in Celsius. So here you see increasing temperature in Celsius is towards the left, whereas increasing temperature is to the right on the bottom x-axis, because a lower number means you're dividing by a smaller number, so your temperature is higher. But the way you convert between the two is you can just figure out that 1.29 is also the equivalent of, what is the equivalent of that in terms of Celsius. So if you know the temperature, 500, you can go and check it, or if you look at the bottom x-axis, 1.29, you can also calculate what the equivalent of Celsius is, because it's not always so easy to think about, okay, well, inverse of 1.29 times 1,000, okay, we're talking about 500 C. That tends to be a little bit more human friendly, but not everybody plots it this way with the upper x-axis. So, that's how you compute between the two. So GDC, people have looked at it because obviously higher ionic conductivity, but why? So here, cerium, you start out with cerium dioxide, CeO2. So cerium is now in the 4+ state because oxygen is in the 2- state, but you have 2 of it. So that's 2-, 4-, and so cerium has to be, +4. If you replace with gadolinium, that's a 3+. And if you look at the ionic radii, it's much closer match than yttria and zirconia. So yttria and zirconia, that's about 17% ionic mismatch. Here it's 7%, so there's a little bit less strain in the material. But of course, some of the downfalls we talked about. Now, the other materials that people have been looking at are all listed here. Essentially, the premise, the motivations are the same. Like, can we have a high temperature, an oxide that has high ionic conductivity, but at lower temperatures? If that's the case, then we can operate our cell at lower temperatures. So it does make a difference if you can operate your cell at, let's say, 400 C versus 700 C. Because the degradation of all the components that house your fuel cell can also be low. The degradation is less. Your cell might last longer. The engineering and manufacturing of the casing also makes a difference in the cost. So I've highlighted here the 3 families of compounds. So bismuth oxide, this lanthanum molybdenum oxide, so LaMox, and also this cocktail of bismuth and transition metal. So bismuth, vanadium, copper oxide. So you start off with a ternary bismuth vanadate, and then you substitute in with some transition metals, late 3D transition metals, copper, nickel, cobalt, all for the same reason. You're trying to introduce introduce oxygen vacancies to increase ion conductivity and stabilize temperature, high temperature phase at lower temperatures. And I can tell you all of these compounds suffer from the same challenges, which is, yes, the high ion conductivity phase works very well, but as soon as you start lowering the temperature a little bit, the materials start to destabilize. They will phase transform into other compounds, or they decompose into binary phases that are not ionically conductive. So that's the main issue with all of these. So, and then the reverse also is a problem, which is you can get high ion conductivity, let's say at a lower temperature, but increasing if you want to use these solid electrolyte, solid oxide fuel cell electrolytes at 500, 600 C, some of the components start to volatilize. So in the example of the bismuth oxide compounds, like bismuth can start coming out of the oxide, and then you have decompositions of sorts. So anyway, that's all to say yttria and YSE and GDC are not the only compounds being looked at. There are, some promising substitutes, other alternative options, but there are quite a number of challenges that these compounds have to overcome to be, viable options as solid electrolytes. I also wanted to note that if you work in the perovskite world, oxide perovskite, I know there's also lead halide perovskites that have come back as viable option for photovoltaic application, although David Mitzi has been working on them since the early 1990s, and then they got abandoned because of amorphous silicon, and now people have come back to lead halide perovskites or metal halide perovskites, replacing lead as photovoltaic materials. So they've had a resurgence. But perovskite materials in general is a huge, rich area of research. I mean, you have such tunability, right? It's a ternary compound. You have tunability of the A site. You have tunability of what's called the B site, although not to be confused with boron, that's also B. So these compounds that contain lanthanum gallium oxide, barium zirconium oxide, or barium zirconate, they're also really promising solid electrolytes for SOFCs. They have high ionic conductivity. You can see here low thermal expansion, which is ideal because when you increase the temperature of your cell, if your electrolyte has too much thermal expansion, right, crack is going to start inducing, and you're going to propagate these cracks the more you run your fuel cells, and then eventually your fuel cell will just short because it doesn't separate the cathode from the anode much more so. So these kind of perovskites, this like LSGM, lanthanum, strontium, gallium, magnesium oxide based compounds, they're a whole lot of fun to work with because there's such tunability. And when you make one change in these perovskite systems, the entire material changes because they're all, you could see in these perovskite materials, they're all corner sharing. So if you substitute one, you're going to cause correlated motions to occur. So you're going to get octahedral tilt, you're going to get rotations, and all these minor changes have huge implications in the macroscopic properties that you measure. So correlated motion in perovskites is a huge area of research. And so this is a rich field. And at OSU, if you go over to Pat Woodward's group, Pat Woodward can tell you everything there is to know about perovskite because he's been doing this research for like 3 decades. So, it's there's a lot of knowledge there, and perovskite based materials as well, so they're used for photovoltaic. You can also use them for like quantum information science. So there's a lot of prospects for perovskite based materials. Okay, so we ranted on and on and on about electrolytes. We'll continue here next time on anode materials as well as cathode materials before we move on to life cycle assessment, sustainability, and the circular economy of fuel cells and the hydrogen economy. With that, have a good weekend. Thanks.